In this video, we'll review two important examples in statistics. One of them is about sum of independent chi-square random variables, and the other one is related to sample mean and sample variance. And the first example will prove that if you add two independent chi-square random variables with degrees m and m, the sum will also have a chi-square distribution of degree m plus n. The proof is very easy, because if you say that this x has a chi-square distribution, its PDF should be this one. If you say y has a chi-square degree, its PDF should be this one, so you can use that. So you see that you have a constant, and then you have x to the power of some half integer minus 1 and so on, and then e to the power of negative x over 2 ux, and same form for that. Now, if x and y are independent, the sum also has a chi-square distribution. Of course, the degree is the sum of the degrees of x and y. So so from here, it is much easier to work with moment generating function. Moment generating function of x is equal to e to the power of sx. Moment generating function of y is e mean of it. And then from the lookup table, you can say this one. And if they are independent, the joint distribution is product of these two guys. So and then the moment generating function of sum is just a product. And if you multiply them, you will see that the degree will be added together. So this moment generating function also has a chi-square distribution, because you see that this is same form as this one and same form as this one, just the degrees are different. The second example is related to sample mean and sample variance of independent normal random variables which have identical distributions. So in this example, suppose that you have n independent normally distributed random variables with mean mu and variance of sigma 2. If you take the sample variance, you remember sample variance, you divide it by 1 over n minus 1, and the sum of a squared of the division to the power 2 from the sample mean. So this is sample mean. Remember, the sample mean and the mean is different. So this mu is the mean, the true mean, and this 1 over n minus 1 instead of 1 over n is because you don't have the true mean, and this is the sample mean. So sample mean, just you average your data, divide by n. This gives you unbiased estimator of mean, and this gives you unbiased estimator of this one. So we want to prove that if you normalize the sample variance by n minus 1 divided by sigma 2, these will have a chi-square distribution with degree of n minus 1. So the proof is very easy. So what you can write is that if you write some of the deviations will become 0. So xi minus mu, you can easily write it like that, because here you could add a minus x bar and then plus x bar, and then consider these two guys together, and then consider these two guys together. So a plus b to the power 2, you will get 4 terms, and then you get this expression. Now you could divide both sides by sigma, so you can divide this by sigma, then you'll have divided by sigma, divided by sigma, divided by sigma, divided by sigma, everything. And then you can apply summation from I equal 1 to n. And so the thing is that this guy has a chi-square degree of 1, because this one is a normal random variable with mean 0 and variance of 1. So its squared value has a chi-square distribution of degree 1. And because they are independent in here, and if you add them together, their degree will be added together. So they have n of them, degree of each of them is 1. So this will have a chi-square distribution of degree n. Now this one, if you write this expression, so this is just one normal random variable with mean of 0. So if you calculate mean of 0, and the variance is 1. So this is inside the square root, is a normal with mean 0 and variance of 1. So it's the squared value has a chi-square degree of 1. Now, and you can also argue that this guy is independent with this guy. So therefore, this should be a chi-square degree of degree n minus 1. So this is a very nice, delicate proof. So you need to show that x bar and y bar are independent. So that means that this random variable, so this is your, this gives you the sample variance. Of course, if you normalize it, this is your y, and these term and these term are independent. So this should have a chi-square distribution if they are independent, because you have the moment generating function of these times moment generating function of these should give you this one. This is chi-square, this is chi-square, so this should have also chi-square. Chi-square is 1 plus, as you have seen in the previous slide, 1 minus s divided by 2 to the power of half a degree or whatever. So sample mean and sample variance of two ID random variables we have here. So if here n is just equal to, we want to see what does mean this theorem that they have said. So if I have two random variables, sample mean is just the middle of the 2 points. So you have two random variables. This is x1 and this is x2. So the center of them is sample mean. And sample variance is just the deviation of from the center. So this guy to the power of 2 plus this guy to the power of 2. And I have to, if you look at it, this distance and this distance are equal. So if I divide it by 2, I get wrong results. So if I divide it by 1, I get this one. So it's kind of like, because this is equal to x1 minus x2 to divide it by 2 to the power of 2 plus x1 minus x2 divided by 2 to the power of 2. So if you do that, then you get these results. So if you and then this is divided by n minus 1, and n minus 1 is equal to 1. But if you would have divided these by 2, you would have got 4 instead of 1 over 4. So now if you take mean of that, okay, if you take mean of that, you will be hopeful that you get your... So obviously the random variables, this random variable and this random variable are independent if they have same. So the reason for this is that if you have two random variables, let's say x1 and let's say x2, if they have identical distribution, length of these vector and length of this vector are equal. So therefore, this is equal to x1. This vector is, so let me make it blue. This blue vector is x1 minus x2, and this, let's say, green vector, because this one is going to be x1 plus x2. If this guy is equal to this one equal to that, these two diameter of this shape should be perpendicular. So x1 and x2 plus x2 should be perpendicular to x1 minus x2, and you know that they are orthogonal, uncorrelated, and if normal random variables are uncorrelated, they should be also independent. So in other words, the sample variance divided by standard deviation, but the true variance has a chi-square degree of 1, because in fact here you have squared of one normal random variables, not two.